Hello everyone, and welcome back to our course on statistical computing in R. So the course is a mix of programming practices, programming fundamentals, R data structures, things like that. And also some theory about numerical methods and algorithms and computers and numbers and things like that. So far, we've focused mostly on the programming side, and we will continue to do that. But from now on, we're going to start introducing more mathematical or theoretical concepts. But we're always going to tie it back to the programming side. So this module, we're going to be talking about the floating point number system. This is one of those things that you really don't want to have to think about. You just want to just assume that the computer is doing the right numerical calculations. And most of the time, we don't need to think about it. So that's a good thing. Computers are very accurate in most cases. But sometimes we do. So for example, I think the main couple of things that you need to worry about in terms of numerical accuracy are things like if you write a new function that computes something quicker than your old function, you did a bunch of optimizations to improve your code, you really need to, like we saw in the last video, you really need to check whether your answer is correct. And to do that, you generally do, some sort of equality test in R. And we saw some of the limitations of that because there's rounding errors and sometimes things aren't exactly equal. So the question is, well, how close does it have to be in order to declare that you got the right answer? And to really answer that question, you have to understand how rounding works in floating point number systems. So is it close enough that the answers differ by 10 to the minus 8? Or does that mean you've made an error in the code? If the answers differ by 10 to the minus 4, is that close enough, or have you made an error in the code? So this is going to depend on a bunch of different factors. And to understand it, you really have to understand how numbers are represented on computers. So that's the topic of today's video. So the major issue is that our mathematical number systems are infinite, and computers are finite. So the integers are an infinite set of numbers. The real numbers are an infinite set of numbers in two ways, in that there's never a largest number, and there's also sort of infinitesimal spacing between numbers. So computers have trouble with both of those things, namely that computers generally do not represent numbers beyond a certain magnitude. And this issue will lead to things called overflow and underflow errors. So in most number systems, there's both a maximum allowable number. Beyond that, everything is infinity. And there's also a minimum positive number, like the epsilon. So if you go over the maximum, you get an overflow error. If you go below the minimum, you get an underflow error. There are also gaps between representable numbers. So the real number system is infinitely dense between 0 and 1. But since computers are finite, there's only a finite number of representable numbers between 0 and 1. And the difference between the numbers that can be represented on the computer and the actual mathematical number leads to rounding errors. So there's been a lot of effort in computing to kind of standardize how numbers get represented, and the overwhelming way that people do it is with the IEEE double precision floating point system. That's what's used in R. So we're going to talk about floating point number systems. By the way, most of this material comes from the John Monahan book, Numerical Methods of Statistics, second edition, and this material is in chapter 2. And it's a lot more detailed, so you can look in the book for more details for all of these concepts. In the notes below, we'll have a full reference to the book. All right, so let's jump into it. So we're going to be talking about the floating point number systems. And as you know, digital computers use a binary number system. They represent data with zeros and ones. But I think let's just ignore that for a moment. What I want to do is describe a floating point number system in decimal. The reason for this is that the actual concept of a floating point number system is actually not that complicated. You'll get it pretty quickly. But I think if you try to convert to binary first and then think about the floating point number system in binary, it's just really easy to get overwhelmed by doing binary conversions in your head and thinking about it. And that conversion from decimal to binary becomes a barrier to understanding what the main concepts of the floating point number systems. So what I'm going to do here is just describe how it would work in decimal, even though most computers use a binary number system, so that you understand the main concepts, and then we'll do it all again quickly in the binary number system. So forget about binary numbers for a second. We're just going to describe a decimal floating point number system. All right. So below right here is a decimal representation of a number. So this is how we communicate, how humans generally these days communicate numbers to each other. So I have 6743.127, which you would usually read as 6,743.127. So what does this representation mean? Well, usually when we learn about numbers in like grade school, we learn about in this format. So what this really means is we take this digit 6, we multiply it by 1,000 because it's in the thousandths place. We take this digit and we add it to the digit 7 multiplied by 100, add it to the digit 4 multiplied by 10, 3 multiplied by 1, 1 multiplied by 0.1, 2 times 0.01, and 7 times 0.001. So this is what this representation really means, is the sum of things. And the reason it's called decimal, 10, base 10, is that the thing you multiply it by are all powers of 10. So we do 6 times 10 to the third, plus 7 times 10 to the 2, plus 4 times 10 to the 1, plus 3 times 10 to the 0, which is 1, plus 1 times 10 to the minus 1, which is 0.1, 2 times 10 to the minus 2, plus 7 times 10 to the minus 3. So all of these things represent the same number, 6,743.127. Now, to store this number, we can think about how you would write it. So we're thinking about how you write it down. Let's think about how you would store it on a computer. So to store this number up here, what we need to do is write down these 8 symbols. So there are 7 digits plus the position of the point. So you would store 6, 7, 4, 3, period, 1, 2, 7 in order. So you have to store these 8 symbols in order. And that's what we had to write down on this page in order for me to communicate what the number was to you. So the storage and this communication I'm thinking of as one and the same concept. We also have what's called scientific notation. So you learn this in school, that you can write this number 6,743.127 in what's called scientific notation, where you put a decimal after the first digit, so 6.743127. These are the same 7 digits, but I've moved the decimal to here. And then you multiply it by some power of 10. And what the power in 10 does is it tells you how many times you have to move the decimal in order to get to the original number that you're representing. So 6.743127 times 10 to the third means you take the decimal and you move it 1, 2, 3 places to here to give 6,743.127. So the stuff in the orange here tells us these 7 digits, and we always operate in scientific notation according to the convention that the point, the decimal point, goes directly after the first digit. By using that convention, that means that we don't have to remember to store the decimal. Really, we could just store these 7 digits plus this part. So the stuff in orange, this tells us the 7 digits. And like I said, the exponent, this 3, tells us how to shift the decimal. So because we're talking about shifting this decimal around, this is why it's called a floating point number system. So scientific notation is one floating point number system. So we just store the digits, and then we plug in the point where it's supposed to be in order to give the original number 6,743.127. So that's why it's called a floating point. And there's one more thing down here. If we want to allow ourselves to have negative numbers in our number system, we also need to store the sign. So whether or not this is a positive or negative number. When we communicate numbers to each other, if it's positive, we don't give any symbol. We just assume that it's positive. But it's negative, we'll put a little horizontal bar next to it to indicate negative. But in a computer, you have to kind of tell it whether it's positive or negative. So we need to store 3 things. The sign, the digits, and then where the decimal place goes. And these are the things that are formalized in a floating point number system. So like I said, in total we need to store 3 quantities, and we represent them by S, E, and F. S is the sign, so that can take on 2 values. It's positive or negative. E is the exponent, so in this case E was 3, and the exponent contains information about where to put the decimal. And then the string of digits, this 6743127, we call the fraction. So this is the string of digits that you're representing. So in our example, 6743.127 represented in sign, exponent, fraction form would be plus for positive, exponent is 3, and then the digits are 6743127. So given this information, our floating point number system tells us how to reconstruct this number. So we take these digits, we shift the decimal from here 1, 2, 3 places, and then we put a positive sign on it. So you're probably wondering at this point, well, why wouldn't we just store this string of digits? This is just way too complicated, going to the scientific notation. Let's just store this thing. We have to store 8 things. That's fine. Let's just do it and be done with it. The issue is that this could be wasteful if you want to store very small or very large numbers. So let's look at this number here. So plus 184362. So this is like, oh geez, well 10 to the 9 is a billion, so it's a square of a billion, whatever that is, which is represented on the right here. So if we were to store this whole string of things, we would have to store 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 with the period symbols in order to store this. On the other hand, here we have to store, let's say, 1 for that, 2 for that, and 4 for that. So that's about 7 symbols to represent this number, whereas there's over 20 to represent it over here. So this could be wasteful for very large numbers because you have to store all these zeros. Now, on the other hand, it can also be wasteful for numbers that are very close to 0. So here's an example where you have a number 3.14 times 10 to the minus 15. So again, it's the same issue that if you want to store a very small number, you would have to store all of the zeros. Here there's a bunch of maybe 13 or 14, whatever the convention is. So the reason for doing this is that we want to be able to store a wide range of numbers with as little storage cost as possible. And what the floating point system does is it balances this trade-off between representing a wide range of numbers, meaning numbers very close to zero, and numbers very far away from zero, very big numbers. So by storing a wide range of numbers, you can avoid these overflow, underflow errors. But it also allows you to store a fine grid of numbers. So if you allow yourself to store many digits here, and in the floating point system, we'll see it's over 50 digits, you can represent very fine grids or differences between numbers as well. And this allows you to avoid rounding errors. So the floating point system kind of tries to manage the trade-off between these things. So it's trying to use the finite representations available on a computer for this infinite number system in a way that avoids errors as much as possible. So we're going to get to the official double precision floating point number system. But before we do that, I'm just going to give a brief refresher on how binary numbers work. And it's really not complicated. I feel like this is more of like a brain block than a difficult concept. It's just when you see numbers printed on a page, you automatically assume that they're base 10 numbers, and it's really hard for your brain to go back and forth between them. But the concept is really not too bad. It's more a matter of reminding ourselves what we're looking at. So to help us remind ourselves what we're looking at, and the book does this too, if there's any ambiguity, we're going to try to give a subscript next to the number to tell us which base we're working in. So this is a binary number because we're saying it's base 2. The ones down here are base 10 numbers because we're putting the 10 below it. Okay, so when we write a number like this, 1011.101, by the way, this is no longer a decimal point because we're not working in a decimal number system. Decimal means 10. So in general, for different bases, they call the decimal a radix point. So we'll just call it a point. So 1011.101 in binary, this works the exact same way as the decimal. So for the decimal, we multiplied each digit by some power of 10 and add them up. For binary, it works exactly the same way, except we replace the powers of 10 with powers of 2. So here this 1 is 1 times 2 to the 3. We get 0 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0. And then after the point, we start doing fractions of 2. So this is 1 times 2 to the minus 1, 0 times 2 to the minus 2, plus 1 times 2 to the minus 3. So there's nothing complicated here. This is just powers and multiplication and addition. And you can see here that these are now representations in base 10 because I'm using the symbol 2 to the 3 and 2 to the 2, which are not symbols in the binary system. So I'm telling you that here with this 10 here. And then if I just add these up, this is 8. That's 0. This is 2. This is 1. This is a half. That's 0, and that's an eighth. So we get 8 plus 2 plus 1 plus a half plus an eighth, which is 11.625 in base 10. So this number is 11.625 in base 10. All right, so that's our brief review of binary numbers. Now we can get to specifying the official IEEE double precision floating point system. So IEEE is a professional organization, and they have various journals and stuff like that, but they also specify standards for things like computers. And so they've defined what they call the double precision floating point system, which we're going to show you here. So it's the same as our decimal floating point system that we described above, but everything is in binary. So we still need to store a sign, we need to store an exponent, and we need to store this fraction, which are the digits. And the number that gets represented is -1 to the sign power. So the sign one binary digit is going to be it's one binary digit, which means it's either a 0 or a 1. So if S is a 0, you get -1 to the 0, which is positive. So S equals 0 indicates a positive number. And S equals 1, you get -1 to the 1, which is a negative number. So S equals 1 is a negative number. The exponent here is going to be offset by 1023. So the reason for that is the exponent is measured in 11 digits. So that means you can go from, in binary, you can go from 0 to 2048. But you want to be able to represent really small numbers as well as really big numbers. So if E is 0, you get 2 to the minus 1023, which is a really small number. But if E is 2048, you get 2048 minus 1023, which is 1025, which is a really big number. Actually, it's up to 2047 is the largest one, I believe. Okay, so that's the largest one. So it would be 1024 would be the largest exponent, which is a really big number. 2 to the 1024 is a really big number. And then the fraction. So the fraction is represented with 52 binary digits. And just like with scientific notation, we always assume that the number is bigger than 1. The number is bigger than 1. So we actually don't need to store the first 1, and we only store the 52 binary digits after the fraction. So this part of the number is going to be like something, so it's going to be 1 plus something times 2 to the minus 1 plus something times 2 to the minus 2. We'll see an example in just a second. Now, if you'll notice, this thing I've written down is a bit of a mess because I'm kind of mixing up binary representations with decimal ones. So E is going to be written in binary, but I've subtracted off a decimal number, 1023. Don't worry about that. I hope you get the main picture for how this works. If not, let's just look at an example here. So here I've written down an SEF, or double precision representation for a number. So this one is the sign, this is the exponent, and let's see what I did here. Okay, so this is the sign, this is the fraction, and this is the exponent. So this has 11 digits, this has 52. I haven't written them all down. Just assume that these are 0, and the sign is 1. So to calculate what this number actually is in base 10, we'll say we do -1 to the sign. So -1 to the 1 is a minus. For here, we're going to do 1 times, we have to do 1 plus. So 1 plus, because we always start with the 1. And then this 1 represents 1 times 2 to the minus 1, or a half. This 0 represents 0 times 2 to the minus 2, which would be a fourth, but we're multiplying it by a 0 here, so that gets left out. And this is 1, it's in the third position, so it's 1 times 2 to the minus 3, which is 1/8. And then the rest are 0. So our fraction part is going to be 1 plus 1/2 plus 1/8. And just to remind you, the 1 comes from the convention that we always start with a 1 here. The 1/2 comes from this digit, the first digit. And the 1/8 comes from this third digit. And then the rest of them are 0, so those don't get represented here. So this is the fractional part. And then the exponent is going to be this number minus 1023. So this number, so this is kind of a long one, but this is, you start on this side actually. So this is 1 times 2 to the 0. 0 times 2 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 1 times 2 to the 10, which is 1024. So it's 1 plus 1024 is 1025. And of course we have this offset minus 1023. So this becomes 2 to the 2. And then if we put everything together, we get minus 1.625 times 2 to the 2, which is 4, which is minus 6.5. Okay, so it's a bit long-winded to explain what this is, but it's really not that complicated. You're just applying this formula, and you have to think maybe a little bit harder than you really should in order to convert the binary to decimal, but your computer's good at that, so you can usually just use the computer for that. All right, a consequence of this representation in binary format is that fractions of powers of 2 can get exact representations. So if you want to represent the number 1/2, you're going to be able to represent it exactly because you'll set this to a 1, the rest to zeros, and then pick this number so the exponent ends up being 1023 minus 1023. And pick this to be 0, so you get a positive, and you'll get a half back. So you can represent fractions of powers of 2 exactly in this IEEE double precision binary floating point system. Now other types of numbers, and we'll see examples of this, like square root of 2 does not get an exact representation. So when you calculate square root of 2 on a computer, could be some rounding error involved. Things like 1/3 don't get exact representations either. Now the last thing in this document that I want to mention are the concepts of the condition of a task or a problem and the stability of an algorithm for completing a task. So this is mentioned at the end of chapter 2 of the Monahan book. And we're not going to go too deep into this. I just want to tell you kind of what these concepts are. We're not going to use these for this week's exercises or labs, but I want you to just be aware of what they are, and they're mentioned in chapter 2, so I'm going to do it here. This is going to become more important when we talk about solving linear systems. All right, so most numerical tasks, also called problems, can be abstracted as you have some output and it's a function of the input. So you want to take the square root. So the input is the number 2 you want to take the square root of, and the output is the square root of 2. So I'm thinking of this as the mathematical function that you're trying to evaluate. Now, there's an important concept called the condition of a task or the condition of a problem. This is defined as its sensitivity to perturbations of the input. So how much does the output change when you change the input by a little bit? So the way this is usually defined in numerical analysis is the following. The condition of the problem is kind of defined like a derivative. So this is the, basically if you took the limit forgetting about computers for a second, you're just doing math. If you take the limit as delta goes to 0 of this expression, this is the absolute value of the derivative. So this is kind of like a derivative. But then it's scaled by the ratio of the input to the output, just for conventional reasons. So this is the condition of a problem. So some problems are well conditioned, some problems are poorly conditioned. So if a problem is well conditioned, that means that the output doesn't change much based on perturbations of the input, or in other words, this derivative is small. If it's poorly conditioned, that means the output changes a lot based on perturbations of the input. For example, thinking about taking the reciprocal of a number. If you're taking the reciprocal of a number near 0, its reciprocal is going to be really big, and changes in the number you're taking a reciprocal of will lead to big changes in the reciprocal. On the other hand, if you're taking the reciprocal of a large number, like 1,000, the reciprocal of 1,000 plus 1 is very close to the reciprocal of 1,000, whereas the reciprocal of 1 over 1,000 plus 1 is very different from the reciprocal of 1 over 1,000. Okay, so that's what we mean by condition. It's a mathematical concept. Now, an algorithm can be either stable or unstable, or some middle ground, of course. Now, we're defining an algorithm as a specific method for calculating this task or this problem. So in general, an algorithm will return f star of the input, so some approximation of the actual input. And the stability of an algorithm measures discrepancies between the algorithm's result subject to perturbations and the actual result. Now, there's no one agreed upon definition of stability, but in general, it will depend on quantities like this. So the algorithm evaluated at some perturbation versus the actual output, or you might look at the output of a perturbed input relative to the algorithm's value at the actual input, or some combination of this. So there's not one agreed upon definition of stability, but generally you're looking at things like this, and generally you're looking at the difference between the algorithm's assessment of what the output should be versus what the actual output is. All right, so I want you to be familiar with these concepts, and we're going to come back and look at them in more detail when we talk about solving linear systems. In particular, we're going to be talking about the condition number of a matrix. So that's it for the theoretical part for this module. What we're going to do now is switch over to looking at some code in R. So I have a script here called numbers.r. It's in the video code directory. And we're just going to look at some of these representations. So in this first loop here, I'm starting with x evaluated at 1. And then I'm going to loop over the numbers 1 through 350. And each time I increment, I'm going to divide x by 10. So x is going to be getting progressively smaller and smaller. And then I'm going to print out both the iteration, j, and x. So let's just do this, and I want to show you what happens. All right. So at the first iteration, x is 0.1, because we divided 1 by 10. And then each one, it gets smaller and smaller. And things are going pretty good for a while. So for the 30th iteration, x is exactly equal to 10 to the minus 30. So this is scientific notation. This means 1 times 10 to the minus 30. And everything's good. X is getting smaller and smaller. The representations appear to be exact. So this 111th iteration, you get 1 times 10 to the minus 111. But as you get smaller and smaller, things are okay. And then you get to about 300, and things start going out of whack. So at 316, the number is 1 times 10 to the minus 316. That's great. But at 317, you start to get these rounding errors. So this is 9.999997 times 10 to the minus 18. And this is due to the finite representation in the floating point number system. There's no number in the double precision floating point number system that's exactly equal to 1 times 10 to the minus 317. The gradations have gotten small enough that you can't differentiate between this number and 1 times 10 to the minus 317. And then you get a few more of these bad ones, and then eventually, once you get below 1 times 10 to the minus 323, you get underflow. So these just get evaluated to be exactly 0. Okay, so this is an example of underflow, a number that's too close to 0 to be represented on the computer. And this happens about in the double precision system. By the way, R uses double precision floating point numbers. This happens around 10 to the minus 323. Okay, so you can see this happen here. So this really should read 1 times 10 to the minus 323, but it does not because of the discreteness of the floating point system. And this one reads as 0, whereas it should read as 10 to the minus 324. Now in binary powers of 2, this happens at minus 1075. So that's that number. So we actually got a number that's a little bit smaller than this one. And I think this is actually, let's think about this, the next smallest number in the double precision floating point system. Let's see, how much do they differ by? Actually, we do that down here. Let's look at that in just a second. And then this one gives 0. And this is how much they differ by. Oh, they don't differ. They're both 0 in that representation. Let's do 10 to the minus 323 minus 2 to the minus 1074. Okay, so you get this number. This is the difference between this and this in the binary system. And I believe this is also, let's see, 10 to the minus 323 divided by 2. Yes. So the gradation between these numbers is this much at this point in the floating point number system. And this is the smallest in E. Now there's a difference between the smallest representable number, which is something like, I think it's actually a little bit smaller than this. No. It's maybe this one. Actually, in the lab, what we're going to do is find out what the actual biggest and smallest numbers are. So we're not going to do that here. But my point is there's a difference between the smallest representable number, which is in this case, I think it's 4.94 times 10 to the minus 324. And the gradation between floating point numbers at different points along the number line. So let's look at an example here. This is sometimes called machine epsilon. So if we look at 1 plus 10 to the minus 15, and then we subtract off 1, well, this should give us 10 to the minus 15, right? If we just change the order of operations, that's what we would get. And that is roughly what we get. So because of the discreteness in the floating point system, we don't get exactly 1 times 10 to the minus 15. We get 1.110223 times 10 to the minus 15. Now, if we try to take a smaller gradation, times 10 to the minus 16, then R is telling us that this is 0. So this quantity is actually equal to 1 in R, or in the double precision system. Now you notice that, so that means that the gradation between numbers, between floating point numbers around 1, the gradation is about 10 to the minus 16, because that's where this change occurs, 10 to the minus 15. It's actually 2 times 10 to the minus 16. But the gradation between the smallest floating point numbers is about 10 to the minus 324, which is a much smaller gradation. So my point here is the floating point system has kind of this mixed precision in that you get smaller gradation between successive very small floating point numbers and bigger gradation between successive larger floating point numbers. So it's important to distinguish between those two in your head. There's the minimum allowable floating point number, and then there's the difference between successive floating point numbers, and these are two different quantities. Actually, just to prove that to you, let's do 1,000. So this I'm going to claim is going to evaluate to 0, and it does, which means that the gradation between floating point numbers around 1,000 is larger than the gradation between floating point numbers around 1, because the system can distinguish between these two numbers, but not between those two numbers. Okay, so that's an important thing to remember. For this main problem of how do I tell if my code's giving the right answer? Well, the answer is that it depends. It depends on the things like the stability of your algorithms and things like that and the condition of the problem. But it also depends on what size numbers are you adding up to arrive at your solution. So that's why there's really no one right answer to determine whether you're getting the right answer or not by checking whether things are equal. So, but the general rule is that you have more precision for smaller numbers and less precision for bigger numbers. All right. So next thing I want to talk about are accumulation of rounding errors. So this is a really important topic that Monahan spends a lot of time talking about in the book. So to demonstrate this, I'm going to try to integrate the normal distribution. So the way I'm going to do that is I'm going to do Riemann integration. Turns out this is really accurate for something like the normal distribution. So I have to pick interval size. So I'm going to step through the normal distribution by 0.001. I have to pick a range of integration. I think there's basically zero mass outside of minus 50 to 50 for the standard normal. This is just the length of x. And then this is the value of the normal density. And to integrate the normal density, basically all I'm going to do is add up the values of y. So it's been appropriately normalized, so we multiply it by the interval length. This is, if you remember learning how to do Riemann integrals, this is how it works. I'm dividing by the normal density normalization constant, and then this is the value of the normal density. So all we're going to do is add up the y's, but I want to demonstrate to you that it actually matters what order you add them up in. And I'm going to do it in 3 different orders. So the first one, I'm just going to add it up from left to right. So start with x equals minus 50 and add up to x equals 50. The second one, I'm going to add up the small values first. So to do that, I'm going to first sort the y's so that the smallest values appear first. And then I'm going to add them up in that order, or add up the smallest ones at the beginning and the large ones at the end. And then here I'm going to reverse sort them. So the biggest ones are at the beginning and the smallest ones are at the end. So let me just demonstrate. So y, these are all, numerically 0 in the floating point system. Sort y. Actually, can I just plot these? Plot y. Okay, that's your normal density. Here I've just ordered those values so that all of the big ones are at the end. And in this one, all the big ones are at the beginning. All right, so let's do the sums. So I'm just doing a very simple R code. I start with the integral being 0. I loop over j equals 1 to n, which is the length of y, and then I add the jth value to it. So if I do that, and then I take the integral minus 1, this tells me what the error is. And the error in this case is minus 4.44 times 10 to the minus 15. So you might say this is pretty good. This is a very small number. But it turns out you can do better by doing the summation differently. Okay, so let's add the small ones first. So now we're adding up in order of sort y. And we get a smaller error here. So what's going on is that if you add up the small numbers first, since there's a finer gradation in the floating point system for small numbers, the errors that start getting accumulated are small at the beginning. And then when you add them at the end, all of the kind of the tiny errors don't accumulate against each other, and the ones at the end don't have a big impact. So this is a better error than this one because it's half the size. And you can see you can make things, I believe you make things worse if you do it in the opposite order. Yes, you get an even larger error. So this is 5 times larger than this one in absolute value. Okay, so the general rule for adding things up is you should add up the small numbers first so that adding a big number to a small number, the errors don't accumulate. But it turns out that the sum function in R is even smarter than that. So if I just use sum of y minus 1, I get exactly 0. All right, so we got to figure out what the heck sum is doing. So let's look at the documentation. Can we make this bigger? Yeah. All right, so let's look at the details. This is a generic function, blah, blah, blah. This is talking about missing values. All right, so here's a paragraph about accuracy. Loss of accuracy can occur when summing values of different signs. This is one of the points that Monahan makes in chapter 2. This can even occur for sufficiently long integer inputs. Okay. Here's the important part. Where possible, extended precision accumulators are used, typically well supported with C99 and newer, but possibly platform dependent. So I think what's going on here is that in our summation function, it's actually using a higher precision than double precision. There's something called quadruple precision. And it seems to me like there's some special algorithms deep in the Fortran code that's getting called that it's using a higher precision than double precision when adding up numbers. So I think that's why the sum function is dead on, because it's using higher precision. So that's summation. Let's look at some more examples where we run into floating point errors. All right, so here's a really common one. We're going to look at this in more detail in just a second. But if you look at this expression, this should be exactly 0. We're taking the square of a square root and comparing it to the number. So square root 2 in math, square root 2 times square root 2 is exactly equal to 2. But in the floating point system, because this is one of these irrational numbers, it's not going to have an exact representation in the floating point system. And so there's an error here. So the error is on the order of 4.44 times 10 to the minus 16. Again, maybe you don't care about the size of an error, but it's not exactly 0. Sometimes you get lucky and get it right, but sometimes not. So what I want to demonstrate here is that here the error is 10 to the minus 13. So it's like 2 orders of magnitude, or no, 3 orders, about 100 times bigger let's see, 500 times bigger. And this has to do with this mixed precision of the floating point system. The difference between successive floating point numbers in this range is larger than the difference between successive floating point numbers in this range, which is why you can get larger rounding errors. Okay, let's look at some more. Cosine of 0, let's see, that should be 1. Okay, that looks good, but let's subtract 1 and see what happens. That looks good. So R gets the cosine of 0 exactly right in floating point. If we look at this one, so cosine of pi over 2, what the heck is that? Cosine of pi over 2 should be 0. And we don't get 0. We get 6 times 10 to the minus 17, which is actually smaller than this, what's called the machine epsilon, which was 2 times 10 to the minus 16. So it's pretty close, but not exactly 0. Let's look at this one here. So if we do sine x minus x, this should be really close to 0 because sine x has this series expansion. It's equal to x minus x cubed over 6 plus x to the 5th over 5 factorial. So if you do sine x minus x, it really should be roughly equal to x cubed over 6, which in this case, if x is 2 to the minus 12, it should really be roughly 2 to the minus 36. But if you run this, you get 2 to the minus 12. Okay, so this is another floating point error as well. Okay, next thing I want to show is how, just to reiterate this point, that the errors tend to grow with the size of the numbers. So I'm going to do this same operation. So above we did square root 2 times square root 2 minus 2. But I'm going to do it for a bunch of different values of j. J equals 1 up to 10,000. And I'm going to plot them. Let's see. Actually, this should say n. And this too. Okay, so let's plot. Well, let's run this first. So this calculates the error. And I'm going to print out the range of the error. So this is the smallest error for these calculations. And this is the largest ones, but 7 times 10 to the minus 12. And what I'm going to do is plot the error as a function of j. And this is what it looks like. So sometimes it gets lucky and gets an error of exactly 0. But in general, when it misses, the size of the error increases with j. So for the largest values of j, the size of the error is something like, well, 7 times 10 to the minus 12. But for the smaller values of j, there's a smaller error. And in general, I think it grows roughly linearly with j. Now let's do the same thing, but we're going to kind of magnify things. So we're not looking at linear in j, we're looking at quadratic in j. So for each j, I'm going to calculate j squared, take the square root, and then multiply it by square root of j squared, and then subtract off j squared. And let's look at this. Here we get no errors. So all of these errors are exactly 0 because I plot the range and it goes from 0 to 0. If we plot it just to verify that, they're all 0. So what's going on here is that R actually can calculate the square root of j squared exactly. So this is the square of an integer. And when you take the square root of that in R, you get exactly the integer back. That's because in the floating point number system, you can represent integers, well, up to a certain value exactly. There's actually, you can't represent all integers exactly. first of all, there's a largest possible number, so you can't represent any integers beyond that number. But because the size of the steps in the floating point system grows with the size of the number, actually beyond a certain point, you can't represent every integer, even before you've reached the infinite value. Okay, so that's just a side point. But up to the ones we've tried, up to 2 to the 16th, you can represent every integer, so you get errors of 0 here. All right, now the last thing I want to show you is computing determinants. Now this is something that has implications for statistics, because in the multivariate normal likelihood function, there's a determinant of the covariance matrix. So this is something I encounter in my day-to-day work as a statistician. And there can be different answers based on how you compute the determinant or what quantity you actually compute. So you can compute the log of the determinant, and that can be more stable. So let's look at what happens here. So I've written a function that takes in a matrix and takes the eigen decomposition of the matrix and then returns the product of the eigenvalues. Now, for covariance matrices, which are positive, definite, and symmetric, this will give you the determinant. So this is a method for computing the determinant of a positive, definite matrix, symmetric positive, definite matrix. And let's see how this works. So I want to create a matrix whose determinant I'm going to compute. It's going to be a 1000 by 1000 matrix. And to get the entries of the matrix, so Aij is going to be e to the minus absolute value of I minus j. So to compute that, I'm using the outer function on 1 over n to 1 over n. And for each pair of these, I'm taking the difference by supplying the minus. And then I'm taking the absolute value of the difference of every pair, and I'm doing e to the minus that value. So that's A. If I want to plot like A 1 to 5, 1 to 5. So along the diagonal, I minus j is 0, so you get e to the 0 is 1. But then things decay as you move away from the diagonal. By the way, this is, it's called exponential covariance matrix, but it's also the type of matrix that shows up in the autoregressive model of order 1 if you've studied time series. Okay, so let's calculate the determinant. Oh, I have to define my debt. So if I compute the determinant, I get a very small number, 8 times 10 to the minus 64. But if you see, if I decrease the value of A, so if I want to take the determinant of A over 10, so it's the same matrix, but all the entries are just divided by 10, I get 0. So in reality, this should be something like, 8 times 10 to the minus 64 times 10 to the minus n. That's how the determinant of a scalar times a matrix works. But 10 to the minus 1000 is a number that's too small to be represented. So you get 0. Okay, so that's a bit of a problem. Same thing happens if you do the determinant of the matrix whose each entry is 10 times A. You get infinite. Okay, so that's a bit of a problem. That's because 10 to the 1000 is an infinite number. So the way around this is you should really calculate, when you're working with numbers that can become very, very small or very, very large. By very, very small, I mean very, very close to 0. You should consider working on the logarithm scale, because then things become more manageable. Problem is there's more than one way to do this, and you have to select the right way to do it. So here I have my log det bad and my log det good. In the first one, I'm doing the exact same calculations, but instead of returning the product of the eigenvalues, I'm returning the log of the product of the eigenvalues. So it's basically the same code except I take the log at the end. And so this one's bad, so you're going to see what's going to go wrong there. In my log dead good, I'm using the property that the logarithm of a product, so log of A times B, is equal to the sum of the logarithm of the individual values. So log of A times B equals log of A plus log of B, which means if you write log of prod, you can replace that with the sum of the log values. Okay, so this is the good one. We're going to see that's more stable. So if we do my log dead bad, okay, we get that number. So this is okay. So this is going to be exactly equal to log of my det A. So that's that number. If we do my log det good, we get the exact same number. So that's good. But if we try to, we know we're going to get a bad answer here. We get minus infinity. That's because the log of my det, well, let me back it up. My det A over 10 is 0, and the log of 0 is minus infinity in R. If we do the good one, okay, we get a reasonable number. So this means that we can think of the determinant as e to the minus 2447, which is a number that's not representable in floating point. Oh, sorry, exp. Okay, so we could still store information about the size of this determinant by working on the log scale. And then the same thing works for big numbers. So my log det bad is infinity because log of infinity is infinity. And my log det good gives us a reasonable number, which means that the determinant is actually this, which of course is too big to be represented, which is why you get infinity. Okay, so the floating point system has inaccuracies in that there's a minimum number close to 0, there's a maximum allowable number, and then there are also discreteness in the floating point system, that there are gaps between successive floating point numbers. And the important thing to remember about that is that the size of the gap between floating point numbers depends on the value of the number. And the gaps between very small numbers is very small, and the gaps between the larger numbers is larger. So those are all important things to remember when looking at inaccuracies or rounding errors and trying to decide whether is this just a rounding error or do I have a mistake in my code. So it's important to know sort of what the rough size of these errors should be when making that determination. And then the other thing is that there are different algorithms to use for computing different quantities. And if you're working with super small numbers, numbers very close to 0, or super large numbers, you can often replace the computation with computing the logarithm of the value instead of the actual value. Okay, that's it for today.